Hi, thanks everybody for coming. It's my pleasure to introduce Bill Hoffman from Kitware. He's here to talk about building science with CMake. Bill?
Thank you, Patrick. Okay, so I'm here today and I'm going to talk about building science with CMake. Now, CMake's a build tool, and normally you think of building software. Quick introduction. My name is Bill Hoffman. I'm one of the 5 founders of Kitware Incorporated. I was the originator of the CMake build tool, and about 5 years ago I picked up running, and so I'm an ultra runner with run barefoot in sandals. So that first picture over on the left is a tech talk I did on CMake, CPEC, CDash that I did about 6 years ago at Google in New York. You can see I don't have quite as many gray hairs. That picture on the right is me finishing a 50-mile race. Quick introduction of Kitware. Kitware is a open source based open science company. We develop collaborative R&D software, and we have several main areas. We have an HPC and visualization, medical computing, a computer vision group, data and analytics, and then right in the middle is software process. And that's really what I'm here to talk about today, is our premier software process tool is the CMake build system, and how it ties all these together and enables science to move forward. We do collaborative R&D software where we create algorithms and applications. We help people with software process and infrastructure. We provide support and training. We play a leadership role in many open source communities. And we work with industry, government, and academia. We were founded in '98. We have offices in upstate New York, that's where I'm at, North Carolina, New Mexico, and Lyon, France. Scientific method. Let's go back to the beginning here. 1637, doubt everything and only believe in those things that are evidently true or reproducible. If it's not reproducible, it's not science. Royal Society, 1640, take nobody's word for it. So an interesting thing has happened since then. Computers and computer software are driving science. In fact, the former NSF director said that software has replaced mathematics as the modern language of science. So in the past, where you'd have equations written out like that, they look more like this today. Whoops, that did not show up. There we go. They show up in code. And to prove that they work, you have to run them. And to run them, you need the data, the input data, and the expected results. And you need to continually refine this. So the great power of software is the many amazing things that we've been able to accomplish with it. But as far as reproducing in science, it actually has a heavier burden, and it's harder to prove that the software is doing the same thing all the time. And this shows up in modern science and a problem. This was in Nature, March 2012. And they found that more than 90% of papers published in scientific journals describing landmark breakthroughs in preclinical cancer research were not reproducible, or just plain wrong. And a lot of this was probably computational. A lot of it was because it was papers that weren't reproducible, and there's all kinds of issues behind that. I won't get into all of them. But reproducibility is key to science. I mean, it goes back to the roots of science. If you can't repeat it, then it's not true. So CMake actually came from an open science background. Now this is a really interesting story, I think. So one of the early projects with Kitware was with the National Institutes of Health, National Library of Medicine, the Visible Human Project. So around 1994, 1995, they created a data set, the Visible Human Project. And this data set, they took bodies that were donated to science, and when they died, they CT'd, MR scanned, and saved those data sets at the highest resolution they had at the time. But then they did something interesting. They froze the bodies and sliced them as thin as they could and took pictures. So now let's imagine you're an algorithm writer that wants to segment the heart out of an MR or a CT scan. How do you know you got it right? You can't cut the patient open. That usually kills them. But in this case, the patient's been pre-killed and cut into many slices, and you can go back and register that. And so they created this data set, but then a Dr. Terry Yu had the foresight to realize that it's not just the data. Providing the data to the community is great and good, but really what you need to provide is the algorithms, because that's where the key is, the algorithms that do the segmentation and registration. Because if you go to like your regular sort of PhD student, right, the professor reads something and says, well, this looks interesting, hands a paper to a grad student and says, well, go off and implement it. You know, here's a neat segmentation algorithm. Go tell me if they did it, if it's useful to us. Grad student disappears, goes off, type. You know. 3 months later, comes back and said, yeah, it didn't work. Did the grad student implement the paper wrong? Was the paper wrong in the first place? There's so many variables there. So Terry Yu had the concept that really what we need to do is take that code, the state-of-the-art in segmentation and registration, and create a toolkit. And it had to be cross-platform, and it had to be easy to use, so grad students and their professors could grab an algorithm, the state-of-the-art, and build on top of it, and not have to re-implement the wheel every time. So in 1999, this project was started, coincidentally, with the start of Kitware, and we were tasked with creating a build system for this beast. And the only parameters we were given is that it had to work on Mac, Unix back then, I think it was more like Spark workstations and things, and Linux, and Windows. So I remember one of the early talks I gave when I was pitching the whole CMake concept. It was at the National Institutes of Health at the National Library of Medicine. I was in a big auditorium, and I was pitching this idea of my new build system. And one of the guys from CMU sort of raised his hand, Bill, why are you creating the ITK build system? It's going to be this weird thing that's different from anything else in the world. It's just this ITK thing. But before he turned it over and let me talk, he said, oh, wait, I think I see what you're doing. You're trying to change the way everybody builds C++. World domination. So that's what really I was like, yep, you got it. That's what we want. And eventually that's kind of where we ended up. But one of the analogies that I like to give, I saw David Abrahams, he was one of the main founders of the Boost project, talk about what drives that project. And he showed a slide with Java and hundreds of really useful classes that come with Java. And then he showed one Python, and here's all these hundreds of useful classes. And here's C#, and here's all this really useful stuff that comes with it. And here's C++, and we have IOStream library. That's it. So Boost aimed to give C++ that rich set of features and also a breeding ground for the next standard. So as things were actually tried in an open source way and a reproducible way, they could make it into the next standards of C++. Well, CMake aimed to give C++ the compile time portability. Now, we can't have compile once and run everywhere like you have with Java or some of the scripted languages, but we can certainly have the same build file that works across all platforms and have that compatibility. And also the ability to take these different libraries and mash them all together and get them to work. And get them to work with a little bit of effort. So the same build tool for all platforms, easy to mix both large and small libraries, and work across a wide variety of computers. And I think so one of the interesting things I like to show on this slide, so you see the big supercomputer there. And the work we did to get CMake to work on the supercomputers actually helped us get CMake to work on phones. Because building for a supercomputer is much like building for a phone or a tablet, because you have to cross-compile to it. The computer you're using to do the compiling isn't the one you're running on. And these supercomputers are essentially a whole bunch of sort of special purpose processors and small OSs. So you're not actually building on those nodes. So that was sort of interesting that this whole HPC thing actually translated into the mobile universe, which became very popular. And CMake is the most popular Kitware tool out there that we do. And admittedly, probably the most boring thing we do. I mean, pretty much everybody hates build systems. And it's got its problems, but it certainly has become sort of the standard because it always has been sort of a pragmatic tool that got the job done. And in 2006, the KDE desktop community adopted CMake as their build tool. And that was sort of an interesting little bit of story there. They have their yearly Academy conference where they get together and decide things in person. And it was scones versus CMake. And there was a guy, Alex Nurendorf, who was the big CMake fan, and there was a couple scones guys. And they met at Academy, but Alex couldn't make it. So the scones guys won. And Alex sent me an email and said, sorry, we lost. I couldn't go. I couldn't make the arguments. And I thought, well, oh well, too bad. Stuff happens. And probably 6 months later, Alex sent me an email. He said, hey, I think we got a chance. It's been 6 months since the meeting, and they still can't build the core libraries in a reliable way on platforms. Because I think if we made our move, people are getting upset now. They're complaining on the developer list. And KDE's always had a philosophy of he who codes wins. So I said, all right. And I took a couple guys at Kitware, and we jumped on it, and we worked with Alex, and in a week we had the core libraries building. And I think in about a week and a half we had it building on Mac OS X. And then probably a couple weeks later we had the core libraries building on Windows. And sort of it took off from there. And it was probably one of the best things that happened to CMake because it brought a lot of structure to CMake and forced us to implement things like proper shared library versioning, proper install things, and to work in a normal Linux environment, whereas we were a little bit more loose when CMake started. And we followed more standards with this. And it also sort of solved the chicken and the egg problem. So you have to have CMake installed to use CMake to build, but people would be upset, well, I don't want to install this extra tool. And one of the things driving CMake is that the requirements I put on is that it would only depend on a C++ compiler. So that's why I didn't use another language or depend on Python, or God forbid, had I picked the language of the day, it would have been Tickle back in 1999. So as bad as the CMake language is to people, maybe it's better that it's not Tickle, because it probably would have killed CMake if it was a Tickle project. But the main dependency CMake has is the C++ compiler. Because I figure rebuilding C++, you're going to have one of those around. And that's done well for us as we've moved to new platforms and allowed it to adapt really quickly. And this shows some how it got sort of 2006. You can see Google search trends on AutoConf and AutoMake get surpassed by CMake. And the other one is an OLO chart showing a number of commits going into projects based on CMake versus AutoTools. So you can see we're growing there. And we get some ridiculous number of downloads a day, like 5,000 downloads a day from the CMake.org. But it's also in all the major distributions. Also in 2014, the company JetBrains wanted to develop a new C++ IDE, and they did some market research to find out what build systems people were using. And they found CMake to be the highest adoption out of they estimated 4.4 million worldwide C++ developer community. So there we go, world domination. So now back to science. Science is not being done by one mad scientist anymore. The problems are bigger. The tools are bigger. You're working from the atomic level all the way up to macro level. And there's software all along the way. Remember, code is the language of science now. And while I was out here at Google, I talked to the robot operating system folks and found out that they have a huge project that has up to 12,000 lines of CMake code. And it's hugely popular and very big. So there's 2,000 packages in their Indigo release. All of those packages, as far as I know, are CMake projects, or at least wrapped in CMake. And they're contributed by roughly 370 different people or groups based on the contributions in their GitHub. CMake makes up about 6% of the code, about 12,000 lines of code for the ROS Indigo code base. I'm not sure whether that's a good thing or a bad thing. But it certainly enables this platform to be created, an open source platform for robotics. Here's the 2,000 packages in their build status. I can't show them all, but they went from A to Z, and there was pages and pages of them. All of them building reliably across, all these different machines. So why would you want to use CMake? So it's easy and it works well. So it's a build system that just works, is what I'd like to say. And it's a build system that's easy to use cross-platform. So this over here is an example I like to use, is the curl library. And you can see their build system is in red. And you can see they've got all kinds of stuff like makefile.watcom, makefile.in, netware, Visual Studio 8, some Amiga thing, a Visual Studio 6 file. And my guess is that at any one point in time, all of those things never worked in their code base. Along the way, people contributed, hey, I got to work on Amiga. Here's the makefile. And they tossed it in there. So it might work. But if it's CMake, you're going to have, a CMake list file in each directory and maybe a CMake module thing directory. And it's going to be a few files. And the project is going to be able to outsource the maintenance of all this stuff to the CMake development team. So that's a huge win for anyone adopting CMake. As long as your platform is on the nightly regression tests of CMake, you're guaranteeing that we're going to maintain it. And as we go forward, we'll know if we broke your code because we're testing it. And if you have a platform that you want to work with CMake that isn't there, you can contribute to our dashboard system and run that. And people have done that in the past. I'll talk about an example a little bit later on. Why use CMake? It's fast. This was from a blog of, was it QGIS? They switched over and they were really surprised that it was quite a bit faster than AutoTools. I think a lot of this has to do with the way CMake works and not using libtool, which is essentially a 3,000-line shell script that figures out how to build shared libraries and complicated things like that. But whereas CMake computes that once and then writes a static makefile or Ninja file that can do it in one fell swoop and doesn't have to figure that out each time. It only does it once during the CMake configure process. Some features of CMake. CMake is actually a open source. It's a obviously open source cross-platform build manager, and it's a macro build tool in that it generates to native tools. So it can use various versions of Visual Studio and various versions of Make. Recently, the Ninja build tool, Xcode. And this, I think, is one of the important features because it allows a project to take advantage of the most important research on the resource on a project, which is the developers. So we got a whole bunch of developers at Kitware, and they all use different tools. They like their tools, right? Some of them like Visual Studio, some of them like Xcode, some of them like Qt Creator. And we can all work together, and everybody can be happy with something like CMake. And you're not taking someone who likes to live in an IDE and forcing them to the command line with some other tool. You're allowing them to use the tools that they're most productive with. And then they're going to be more productive on the project. And it allows greater collaboration. So CMake supports a whole ton of operating systems, and we're constantly adapting it. It's got platform introspection commands, so you can search for programs, libraries, or packages. I like to say I like to see code that sort of programs to a canonical system, not a specific system. What I mean by that is instead of having if def Linux version 5, 6, 7, then add, you can call this function. I'd rather see a try compile in the CMake side and then something that just says, if this function is available, then use it. And that way your code's going to be portable going forward. So you can also do compiler feature detection we've added. CMake also adapts quickly in new technologies. So as new versions of Visual Studio are released, we're jump right on them, or someone in the community jumps on it. Same thing with Xcode. Ninja's a great story. So that was the build tool that was created for building Chrome, I believe, through Google. And it's a command line tool, and it replaces Make, and it does a really good job of doing parallel builds. And I think within a couple months of it being public, there was a CMake generator donated to CMake. And then I think we got it sorted out probably in another couple months after that and got it working on all of our platforms and passing all of our regression tests. We also, when new compilers come out, we support those and understand how to use them, different GCC versions, Clang compiler. We support complex custom commands, so we can do things like build CUDA or Qt's mock. Or originally, this all came from VTK, the Visualization Toolkit, which has the ability to wrap into multiple languages. And that's like one of the toughest things for a build system to do. Essentially, we had to build a program and then take that program and give it more input that builds more source code that then has to be built into libraries. So we had to support that on all these different IDEs and different build systems. So CMake's always had the ability to do very complicated commands from the beginning. Building shared libraries, configured header files. There's single input for all platforms. It does automatic dependency generation for C, C++, and Fortran. Full dependencies, build target in the same directory. We handle out-of-source builds and parallel builds. The CMake support has many features, including color progress output for Make, the ability to auto-rerun CMake if any CMake input files change. This works in Visual Studio as well. And the idea there being that you run CMake once, and then after that you really don't see it again. You just run your native build tool, and as you change files, the build system will update itself automatically. It's got a full cross-platform install system. Okay, so CMake provides various forms of documentation. There's a book for sale, there's a web page, a wiki, a very active mailing list. It ships with HTML, man pages, and command line help. We recently created a restructured text and Sphinx system for generating the documentation. CMake also has what are known as cache editors. So in the CMake project, it creates a cache which stores persistent variables and the results of things like try compiles and your system introspection in a file called the CMake cache. And this also has things to turn on optional parts of the build. So you can go into a GUI and create things like, build with MPI or things like that, and it shows up in this GUI. There's a curses one and a Qt one. So if you don't have a windowing system, you're on some sort of supercomputer or something like that, you can use the curses one. And of course, you can run CMake from the command line with no options, or you can pass in options as well. You can run CMake in script mode. There's also a CMake -e command, which supports things like copying files and sort of things that you might have in your shell, and we don't want CMake or CMake builds to depend on a particular shell because we want it to be cross-platform. And you can write scripts and run CMake in that script mode. In that mode, it just doesn't generate the cache and doesn't do anything specific to generating the build. CMake also has, although I'll call it a newer feature, the idea of CMake packages. And these packages can export targets. So normally when you're building in CMake, if you add a library and executable, those are called targets. And they're part of your build. And if you've added library A somewhere in your project, you can say target link libraries my executable to A, and then A will link to that library. But if A was built in a completely separate build of CMake, or maybe even not with CMake, you can now pull it in with what's called an imported target, which is just basically a little bit of code that describes, where that file is, what the debug version is, what the release version is, what includes you need to do to get to use that object. And CMake supports this. There's a package config helper that helps you write your own CMake packages. And Qt5, so although Qt does not use, or Qt does not use CMake as its build system, they do ship with CMake config files. So they make using Qt with CMake very easy. You can go in and say find package Qt5 widgets, add executable hello world, and then target link libraries Qt5 : widgets. And that's going to pull that imported target in. And they're maintaining it. And this works out much better for the CMake development community because we don't have to put a find Qt module in CMake and get out of sync with their releases. It actually gets released with their code, and CMake knows how to handle that. Another newer feature is usage requirements. So originally, CMake had a very sort of autocomfish, directory-centric view of the world. Right? That's how make files were, and that's how it was when we created it. Is that you had each directory had some libraries and executables, and pretty much the include flags and all that went with the directory. And you sort of inherited this recursive directory structure. But CMake's moved away from that, and the target is now sort of more object-oriented view of the world, where a library or an executable can propagate its include directories or compile definitions and more. So target link library and target include directories, you can specify public and private or interface options to them. So for example, down here on the bottom, I'm doing target include directories, foo interface, zlibdir. And now anything that links to foo will automatically have zlibdir on its include line. You can also have compile options and compile definitions done in the same way. You could also have, say, a private compile option. So say I've got some third-party library that I'm building with CMake, and I don't want to go in and clean up the code, but I want to use, f no unused parameter. I can set that library, and I can set as a private thing. So if I link against that library, it doesn't pull that compile option with it. It just sticks to that library. Whereas if I want to add ndebug to anybody that links to foo, I can do that this way with compile definitions. We've also added compiler feature detection to chase the ever-evolving C++ standards. And so you can write your C++ code to a canonical system and handle various different compilers. Another feature that's been in CMake since 2.8, but many people don't know about it, is an external project feature. We did a Kitware source article, and this allows you to either download or pull from a version control system a completely separate package, or undo a tar file and build that as its own complete project. And we put these together, and this is important for this effort of pulling together these giant systems. And this was funded by the Army Research Lab. They created something called the Computational Science Environment. And it was a package of 100, 200 packages that they wanted on their HPC systems. And they were building them all with CMake, but they didn't want to rewrite the build system for all of them. So external project can actually build things that aren't built with CMake. It can run auto tools, it can run other things, it can run QMake. Essentially, you give it the configure command and the build command, and it can be set up in a cross-platform way. Here's an example of a project that uses Google protocol buffers, CLAPACK, VTK, Qt, Trilinos, curl, and Boost. And then I can see this in a Visual Studio project. Now I'm going to talk about test data management and external data. So along came distributed version control, and it's meant for source code, not data. So you have a local history of source is great. You're often modifying its interesting history. You can do things like log and blame. But a local history of data is actually bad. It's rarely modified. It's got a fairly boring history. Whole file commits with poor deltas. And there's no real blame on a binary file. It's just so-and-so checked in this. And it's one big lump. So it really doesn't fit in distributed version control very well. So separating the data from the source. The source must reference the data. Tests need matching data. And this is important because the tests and the data go together. And early on, we struggled this with VTK. We had separate repositories. There was like a VTK data and a VTK. But if you checked out the wrong version of VTK data, well, all the tests might start failing, or some of the tests might start failing. So they really need to be bound tightly together. And actually, distributed version control and things like Git gave Brad King the idea that he could implement something called external data in CMake that could use hashing to content address storage to have your data in arbitrary locations. Could be on a local machine, private server, internet server, and the content gets verified by hash. So no need to trust the provider if the hash is strong. So the external data module is part of CMake. You start with real data in a source tree locally. You can change the source code to reference the data by the original file name. And then you can create it as a content link, which has the hash. And then thus have your data stored elsewhere and be able to pull it in. And this supports various modes of place of storing the data. And in fact, for the Google Tango project, we added Google Data Store to it and the ability to add plugins very easily to pull in from different data stores. The build system does this on demand, so it can fetch it during the build. It can download your data, or you can force it to download it by building a target that you put. And uses local instances by file name. The original file name could be provided by a symbolic link if possible on the operating system. So the external data, the method is sort of a black box. Somehow it's going to get it. You can configure a list of URL templates and try them in order. So some things coming to CMake. We'd like to generate Android MK files, so you could do a cross-compiled build onto Android using CMake tool, and then have all these libraries that are ready to go on Android. But then if you wanted to mix them into an Android project, you could have CMake generate Android MK files that point at existing libraries and then make it easier for the Android developer to use your large tool that's built on CMake. And also, we're working on integrating the Android platform support, simplifying the Android toolchain that's been passed around the internet from OpenCV fame and used in many, many projects. And I think we can simplify that and move a lot of that code into CMake. Here's a simple example that sort of shows the power of CMake. It's a simple project, an executable that does pretty much the full gambit of CMake things. It creates an executable, and it links to Qt and installs required system libraries and creates a C package, which is nice. But then I added 4 more lines of code, and now I'm using Boost as well. So this is a powerful tool for developers to use the rich set of C++ tools that are out there. Now I'm going to talk a little bit about testing. So automated testing is obviously important. This graph shows automated testing versus manual testing and how much time it saves. It seems a little bit obvious here, I guess, but if you're manually going through some test suite, you're going to keep adding up that manual labor every time you do it. But if you have an automated test system, you're not continually adding time to the project. Although, unfortunately, probably what happens is the same amount of time gets spent, it just gets tested less. So we have a project called C-, which is an aggregator of test data. And it can show you different builds. It can do things like image comparison here. You can see it does dynamic analysis and code coverage. And this actually came out of Six Sigma at GE. So before I was at Kitware, I was at GE's research and development. And this was back when Jack Welch had a big Six Sigma push. And he pushed the whole company had to do Six Sigma training. So right down to the secretaries and everybody at the research center. And this was a process created by Motorola to create, chips on a mass scale where your errors and defects would be in the Six Sigma. But if you've got a company like GE and you want them to move in a certain direction, you make everybody do it. And of course, all the scientists at the research center were whining and screaming and saying, this is ridiculous. We write papers and throw away code. How does this apply to us? But there were a few of us there that were sort of software geeks that said, hey, this might be a neat way to get some funding or time to do some software testing stuff. And we created the idea of a dashboard. So I'll go back here. So that the idea there is, what can you measure in software? Well, you can't measure defects because you don't know what they are, but until you actually find them, and then you'll fix them. But you can measure things like number of build warnings, number of build errors. You can do things like static or dynamic analysis. You can do code coverage, and these are all things you can actually measure and try to drive down to zero. C- can be used with other tools. On the Project Tango that I'm here for and others, they use Jenkins. At Kitware, we're experimenting with using BuildBot on the ParaView project, and we've extended it to run, configure, and build test steps for CMake. And BuildBot can parse the output of CTest to determine error and warning status. People have used Travis and CircleCI. Essentially, it's a great aggregator, and it works great on giant open source projects because other people can contribute. If they aren't, it's very unlikely you're going to get someone to contribute a machine to your Jenkins build farm. But you can probably get someone to run a cron job once a day that'll build your software if they're getting something out of it, like their platform's guaranteed to work with CMake going into the future. We've also done C- integration with GitHub, GitLab. Testing with CMake is fairly trivial. You include CTest. You call add test. It gives you a test name and executable, and you give it some arguments. And the test will pass if it returns 0 or non-zero, it'll fail. You can also set up regular expression parsing of the output. And then it can be sent to C-. Here's a quick video of ParaView nightly testing, running, showing that CTest can run in parallel. It's running like 8 different copies of this. And that's doing screen grabs and image differences along the way that then get reported to C-. Originally, the Trulinos project was a Sandia project for solvers, and they created a multi-package dashboard. And this allows a project to have many projects, because you might be working on, say you're one of the ePetra guys, you really don't care what the Tethos guys are working on. And if they broke their dashboard, you don't really care. You only care about your stuff. You might care about theirs, but you more care about your stuff. And this way, it lets a large project divide it up and look at the different sections. Can do coverage, gcov, bullseye, Valgrind, and Purifier supported. And again, it provides a nice way to get down to the details of these instead of looking at huge log files that might be produced as some build artifact. It can send you nastygrams when you've broken the code. It has nice wrappers of the output, so you can see exactly what the command line that was used to build and what the standard error, standard out were. You can set up query filters on C- to look at certain things, like sometimes I've looked at a particular machine over a month's period of time to see when things started going bad. We've added a lot of support for Clang-based tools, so thread sanitizer, address sanitizer, memory sanitizer. Include what you use, scan build. And this allows this process where you have developers and users. They look at the code. It goes to some software repository. There's some build, test, and package system that then goes back for community review, and this cycle continues. And that's really an open source, open science thing that's enabled by CMake and C- and these testing tools. Also, we have a tool that's part of CMake called CPack, which can create installers in much the same way we create build tools. So you can create, a Visual Studio installer, a Mac installer, does drag and drop, plus the other Mac installers. Supports just creating tar.gz files, nullsoft installer, Wix, Mac OSS, drag and drop, plus package manager. Debian and RPM packages. Using it's really easy. The first step is you get your install rules to work, so it creates a tree that's going to work, and then you include the CPAC and maybe set a few options before you include CPAC. And then again, this is one of the design philosophies of CMake, is to take these sort of mysterious things like creating an installer. When we first had CMake, there was one guy that knew how to make the installer, and it worked on one machine. And if he was out or that machine was down, we weren't making CMake releases that had the installer. Right? So being able to abstract that stuff out and sort of take the black art out of weird computer science things that usually there's only one guy that knows about, and codify it in the build system is part of what CMake does. You can do component-based installed. So now I'm going to sort of give a whiz-bang tour of where CMake has had an impact on science. So in the beginning, for Kitware, there was VTK, and that's the Visualization Toolkit, and it's, grew the whole company, and it obviously builds with CMake. The Google Project Tango, which is why I'm here at Google right now, is a really cool project where they're creating a mobile-based system that can scan the 3D world around you and know where it is in that world. And it's a really exciting project, and I'm really grateful to be a part of it. And the reason we got pulled into that project is because of the build tool CMake. They were using CMake-based build system, and they pulled Kitware in to help with using the build system and doing some analysis. And Project Tango is a huge community effort with lots of partners and lots of dependencies. So this is a graph of the sub-project dependencies. Remember I talked about the sub-project builds that C- supports. Well, it allows you to view all those sub-projects and their dependencies. And this is a view. Obviously, you can't read them all. There's tons of them. And we also have a data storage system called Midas, which can store data. And then we created, originally for our computer vision group, we created what we call the tracker. So one of their big algorithms is tracking things in computer vision. So you're watching cars move around an aerial surveillance video, and you're tracking them. But they want to know if their tracker is getting better or worse over time. So they created this way of uploading the data, and we're doing the same thing for the Tango project. And you can see here, we've taken the sparse mapping algorithm, and we've basically got it down to one number that's the error. And at some point in time, you can see that things got worse. But that's all right that it got worse, and because then we can go in and drill down at that data and see what happened when it got worse. And we can see where it went. And then we can even get back to the C- dashboard, and we can get to the commit that caused it. And then we can make things get better again. Another project is the Computational Model Builder and Reactor Geometry Generator projects. This is a framework to easily adapt specific problem domains. And it's all developed under a BSD license. It uses various simulation codes are supported. And the libraries used in the Computational Model Builder, pages of them. And this is all built with the external project and CMake. The Reactor Geometry Generator provide an easy set of tools to model mesh generation component applications that support various nuclear energy workflows, supporting various HPC environments, and leveraging other existing efforts being developed within the DOE. And of course, got really nice pictures out of it, so got to put some slides in. And again, it uses a ton of libraries, and they're all compiled and built and follow this rigorous testing structure that we talked about. Here's another one, a project that we worked on called Virtual Pediatric Airways Workbench. And its dependencies, VTK, ITK, VPN, RN, JSON, CeloPack. It's a 3D interactive way of editing airway geometry with 3D input voices to look at possible surgical outcomes. So in this case, preoperative, we can see there's a problem. The the airway is choked. And then they did surgical modeling, and that's what they wanted it to look like. And post-operative, then they can compare and see that they actually got what they wanted. So it's an interesting application of science. And again, it's depending on this built system infrastructure and testing infrastructure. This was an interesting one. I've never met these folks, but they're at, down in Australia, and they had these big autonomous mining robots. And they use QNX, and they use CMake, and they came to me, one of them emailed me and said, oh, I want to use the QNX system for CMake. And I said, well, that's great, but you're going to have to provide dashboards for it. Because if I just take what you give me and stick it into CMake, probably 6 months later, we're going to break it. And they said, no problem, we'll set up dashboards. And they set up continuous dashboards. And I remember one time there was something wrong with shared libraries on QNX. And because of the time zone difference, I couldn't really talk to them or chat with them. And I just checked in some extra print stuff, and I checked in CMake, and I'd wait 10 minutes. And I'd look on the dashboard, and there would be the build. And I'd look at the output. And I was able to actually debug something and get it working without even console access to the machine because they had contributed that dashboard. ParaView is another big project at Kitware. It's an open source, multi-platform data analytics visualization tool for analyzing extremely large data sets. This was also one of the projects that got started early on with Kitware back in 1999. Los Alamos came to us and they wanted to use VTK on parallel systems, and they paid us to add MPI support. And then they wanted an end user tool, which turned into ParaView. ParaView is an open source project, and they're using BuildBot. You can see sort of lines of code going into ParaView, and then the ParaView dashboard, which uses CDash and then BuildBot to drive that. It makes data analytics and visualization software. And it depends on a whole bunch of libraries and various specific versions of those libraries. And this is all maintained and controlled with this external project. There's about 60,000 lines of CMake code, so it's even bigger than the robot operating system. Broad set of dependencies, cross-compiling support, BlueGene, Q, Cray, XK7, Windows. Another project is 3D Slicer. This is a medical application for doing image analysis for medical research. Uses VTK, ITK, CTK, Qt, Python, a whole bunch of other stuff. The key infrastructure is CMake, CTest, CDash, GitHub. Distribution mechanisms, it's got an extended manager for distributing software, and a lot of this is all maintained and wouldn't be possible without an open source build system like CMake. And it uses a ton of packages. And it has a whole bunch of interesting clinical projects that have been used. I won't go over all of them, but surgical navigation, prostate procedures, radiation dosage calculations. So a lot of interesting, important science going on. This is one example I pulled out, and it's a case study built on top of Slicer, where they grad student and professor designed some robotic hardware for improving preclinical ultrasound imaging. And again, this is all possible because of the boring build tool, CMake. Another interesting person, the group that came to us, we have a source, sort of a magazine that we produce at Kitware, and we invite outside contributors, and someone from Netflix actually showed up and wrote a whole article on how they're using CMake for their SDK. So whenever you see the Netflix inside on your Blu-ray player or different device, some vendor had to use the CMake generated SDK for that. And they use CDash as well. The Kitware Computer Vision Group works on aerial imagery mostly. They do event and activity recognition. And they're working on some open source tools. They're creating a new toolkit called Quiver, which is an open source platform for production quality video exploitation. And again, this is using Boost, OpenCV, various packages. And they've created a system called Fletch, which uses CMake to build and compile all these different C++ libraries and other libraries and create development environment. We've got MapTK. Again, it's another tool. It's an open source BSD thing that's created by the computer vision group at Kitware, and this is open source for optimized for aerial video processing and can use a GPU and do motion imagery aerial photogrammetry toolkit. So we just celebrated 15 years of CMake. It had its birthday about 15 years ago. That was when I started it in like 2000. Over that decade and a half, it's had a huge impact on scientific efforts involving C and C++. Building science with CMake. So I think I made the point that science involves reproducibility, and builds are part of that reproducibility, integrating with continuous integration tools. And it's bigger than that. It also includes the data and the algorithms, and being able to test the data and the algorithms and tying that all together. And there's many domains that touched on: medical imaging, computer vision, robotics, nuclear energy, and there's many more. I mean, it's an open source project, so it's kind of hard to tell who's using it and who's using it for what. Open source is enabling the use of many collaborators as well. So I'd like to say thanks to my hosts here at Google. Thanks to the many, many contributors to CMake, the awesome developers at Kitware, the Google and Google Tango project.